Hi there. Today our topic is an analysis of Dolby Audio. We will talk about Dolby Audio's reality, different types noise reduction, audio coding and compression, and image processing. First part, I will introduce how does multi-channel achieve nature hearing. To begin with mono, there is only one signal. The same signal can be reproduced through many speakers, but you will only hear a same voice. In two-channel stereo, there is a left channel and a right channel. Two different signals transport to different speakers. In this way, it can produce a stereo, but it is still not real enough. Dolby Audio has two famous multi-channel technologies, Dolby Digital and Dolby Digital Plus. The Dolby Digital is a 5.1 channel system. It has left, center, right, left surround, right surround channels, and a low frequency effects channel. The low frequency effects channel processes low frequency audio signals, and it occupies 1/10 bandwidth of each of other channels. Therefore, it needs 5 speakers to process. The Dolby Digital Plus is an improved system based on Dolby Digital. It uses 7.1 channels. The difference of 5.1 channels and 7.1 channels is that 7.1 channels has 2 more channels, back surround left and back surround right. So it needs 7 speakers. And then here is a Dolby Digital Dolby Audio demo. It shows the effect of Dolby Audio.
So let's start with audio noise reduction. A Dolby noise reduction system is one of the series of noise reduction systems developed by Dolby Laboratories for use in analog audio tape recording. In this section, we will talk about 4 Dolby noise reduction systems in timeline and how Dolby implemented them. Among those systems, Dolby A was developed for professional use. Dolby B, C, and S were designed for the consumer market. Dolby A-type noise reduction was the first noise reduction system developed by Dolby Laboratories, presented in 1965. The original unit was designed to be a noise reduction system for use in professional tape recording studios, where it became commonplace, gaining widespread acceptance at the same time that multi-track recording became standard. Dolby A introduced a refined version of audio compression and expansion technique to dramatically reduce the background haze inherent. It has two stages. The first is the encode stage, or the recording stage, and the other one is the decode stage, or the playback stage. The encode stage dynamically increases the top end of a signal without introducing artifacts or altering the harmonic content. The input signal is split into 4 frequency processing bands. This provides about 10 dB of noise reduction. Dolby B-type noise reduction was developed after Dolby A and presented in 1968 as a single sliding band system providing about 9 dB noise reduction to address the haze of slow-speed consumer tape recording formats, primarily cassettes. Dolby B recordings are acceptable when played back on equipment that does not have a Dolby B decoder, such as most inexpensive portable and car cassette players. However, Dolby B provides less effective noise reduction than Dolby A. Without the de-emphasis of the decoder, the sound will be perceived as brighter as high frequencies are emphasized. It is very important that the use of noise reduction not take away from the ability to record loud sounds by unnecessarily boosting them. Loud sounds already hide noise on their own, so any increase would only mean that the overall recording level will be turned down to prevent distortion. Therefore, Dolby B applies the principle of least treatment in its design. Least treatment says if there's no benefit to be gained by changing the audio signal, then don't change it. This means that the loud signal are not processed, so there's no chance of causing tape overload when noise reduction is being used. In Dolby B, the noise reduction system includes 2 steps. Step 1. When music is being recorded, it is encoded just before reaching the tape. The purpose of encoding is to raise the level of soft, high-frequency passages so they become louder than the tape noise. During the trip through the Dolby encoder, loud passages are not altered. Soft, high-frequency passages are made louder than normal as they are recorded on the tape. Step 2. When playing back on the tape, the sound is decoded by a precise mirror image process of the encoding in Step 1. The loud sounds are left unaltered, while the soft, high-frequency sounds are lowered back down to their original levels. This is where the noise reduction occurs. During the decode stage, tape haze is added to the recording during the recording process. In Step 1, the Dolby encoder boosted the soft, high-frequency passages before the signal reached the tape and before the tape haze was mixed in. And in Step 2, as the Dolby decoder scans the signal coming off the tape, that tape noise has been added to the music. However, when it is reducing the decoded sounds to their original levels, the noise automatically getting the same treatment. As a result, it completely restored musical balance, but with less haze in the reproduced sound. Dolby C was introduced in 1980. It used the same noise reduction strategy as Dolby B, but it combined the effect of 2 Dolby B systems together with an expansion to lower frequencies, which provided 20 dB of noise reduction above about 1000 Hz, fully doubling the amount given by Dolby B. One of the Dolby C's features was that, comparing to Dolby B, Dolby C had an increased noise reduction bandwidth. As you can see from the graph, Dolby C-type noise reduction begins to take effect in the 100 Hz region and provides about 15 dB of noise reduction around 400 Hz and 20 dB in the critical 2000 to 10,000 Hz area. By starting 2 octaves lower than Dolby B, what little noise that is left again appears to be spread evenly over the frequency range and therefore is not noticeable. Another feature of Dolby C was the dual-level processing. In the previous slides, we mentioned that the Dolby C provided 20 dB of noise reduction above 1000 Hz. The fact is that covering a full 20 dB of processing range with a single sliding filter leads to problems such as overshooting and overstressed manufacturing tolerance. Dolby C solved those problems by using 2 sliding bands in a special way. Both bands cover the same frequency range but are sensitive to signals at different levels. One of the 2 bands is sensitive to signals at almost the same level as a Dolby B processor, while the other band is sensitive to signals at a lower level. As one filter reaches the end of its sliding range, the other one gradually takes over. Each one provides 10 dB of compression and expansion. They are connected in series, so their effect added together to provide 20 dB of compression and expansion, and as a result, 20 dB of noise reduction. Dolby S-type noise reduction was the culmination of over 20 years' experience in the design of noise reduction systems. Dolby S was designed to continue applying the least treatment principle, but in some powerful new ways. Even though it provides even more effect than ever before, the Dolby S processor devotes much of its energy to not processing the audio signal. In other words, more effect with less visible effort. Just like Dolby C, Dolby S used 2 high-frequency sliding compression and expansion bands, but in addition, each band is coupled with a separate high-frequency fixed-band processor. This technique was called action substitution. By using such technique, Dolby S-type noise reduction was able to provide 24 dB of high-frequency noise reduction.
So for this part, we're going to talk about audio coding and compression technique of Dolby AC3. First of all, what is Dolby AC3? Dolby Digital, also known as Dolby AC3, is named for audio compression technologies developed by Dolby Laboratory. It is based on modified discrete cosine transform algorithm, DMCT. It is initially provided for digital sound in cinemas, but nowadays it's also used for other applications such as TV broadcast, radio broadcast, digital video stream, DVD, Blu-ray discs, and game consoles. After the introduction of Dolby AC3, now we're gonna do an introduction of AC3 coding technology. AC3 is a frequency domain coder which take advantage of phenomena of psychoacoustic masking. The time domain input signal is transformed into frequency domain, and the frequency domain coefficients are adaptively quantized. The first technique is filter bank. In signal processing, a filter bank is an array of bandpass filters that separates the input signal into multiple components, each one carrying a signal frequency subband of original signal. And the second is the spectrum envelope. A spectrum envelope is a curve in frequency amplitude plane derived from a Fourier magnitude spectrum. It described one point in time. And the bit allocation. AC3 employ a unique hybrid forward and backward bit allocation algorithm The core of the bit allocation routine is backward adaptive. In the code spectrum envelope is used by both encoder and decoder in order to compute the bit allocation. And the last is coupling. When audio is encoded at a very low bit rate, audio quality will be suffer. AC3 can provide high audio quality for bit rates of approximately 80 to 96 kilobytes per second per independent channel for critical material. When a multi-channel audio program is encoded, further saving in bit rate can be achieved by invoking the technique of coupling. So after talk about Dolby AC3, now we're going to talk about Dolby True HD. So first of all, what is Dolby True HD? Dolby True HD is a lossless multi-channel audio codec which is mainly used in home entertainment equipment such as Blu-ray disc players and AC receivers. Dolby True HD used Miranda's lossless packing (MLP) as its mathematical basis for compressing audio samples. MLP is also used in the DVD audio format, but details of Dolby True HD and MLP lossless format as used on DVD audio differ substantially. And more importantly, Dolby True HD is one of the successors to the Dolby Digital AC3 surround sound codec. And why Dolby True HD is so unique compared to other lossless audio coding formats such as FLAC, MPEG, capable to lossless AAC, and audio lossless coding. True HD is unique in that, in addition to being lossless, it has a hierarchical, scalable bitstream structure that facilitates low complexity decoding of downmixture presentations of the source multi-channel signal. So after that, we're gonna see a simple view of True HD system.
Before we get into Dolby Vision specifically, let's quickly recap HDR in general. High dynamic range is a technology that lets filmmakers and content creators produce videos with increased brightness, greater color accuracy, and better contrast than what was previously possible. While HDR is often utilized in high-quality theaters, it's also become increasingly popular for home viewing. When HDR content is viewed on a quality HDR-compatible TV, you can tell right away. The increase in overall picture quality is dramatic, offering a touch of cinematic quality on the small screen. As touched on above, Dolby Vision is a proprietary dynamic HDR format developed by Dolby Labs. By adjusting the picture on a scene-by-scene and even frame-by-frame basis, it lets you see more detail with better color accuracy. It is constantly making adjustments so that each image on the screen is optimized, but there's more to it than that. From the picture, you can tell the difference with and without applying Dolby Vision on the original sample picture. The left half part gains more contrast and brightness than the right half. In addition to the ability for content creators to tweak picture settings at a highly granular level, Dolby Vision supports a much wider range of possible settings than the more conventional and static HDR10. For instance, HDR10 supports a maximum picture brightness of 1000 nits for TVs. Dolby Vision can go much brighter, up to 10,000 nits. The same is true for color accuracy. HDR10 lets content creators specify color using 10 bits of data, whereas Dolby Vision supports up to 12 bits. That spec might not seem like a big deal. After all, that's only a difference of 2 bits, but it makes a huge difference. With 10 bits, you can pick from among 1024 shades of each primary color, which gives you over a billion total possible colors. Again, that sounds huge until you realize that 12 bits give you 4096 shades and a total of over 68 billion colors. If that sounds like an overkill, when it comes to a TV, it is. For the moment, there are no TVs you can buy that are capable of displaying 10,000 nits of brightness or the 64 billion colors that Dolby Vision provides. Even the brightest TVs on the market tend to max out at 2,000 nits of brightness, and not even LG's OLED E-series offers better than 10-bit color support. That said, TV technology is advancing very rapidly, so Dolby Vision's current above and beyond specs may seem perfectly reasonable in another 5 years. Dolby Vision is considered more precise than HDR10 in that its HDR parameters can be encoded scene by scene or frame by frame, and it can be played back based on the capabilities of the TV. In other words, playback is based on the brightness levels present at a given reference point, such as a frame or scene, rather than limited to the maximum brightness level for the entire film. Another advantage of Dolby Vision is that the metadata is embedded into the video signal, meaning it can run across legacy HDR connections as far back as version 1.4b. Despite only using static metadata, HDR10 requires HDMI 2.8 compatibility. On the content production side, Dolby Vision seems more focused on pushing HDR to its technical limits. The minimum specification for Dolby Vision mastering requires the use of reference monitors with a contrast ratio of 200,000 to 1, peak brightness of 1000 nits, color range approaching the REC 2020 standard, and support for the SMPTE ST2084 HDR format. In other words, a Dolby Vision TV also has the ability to decode HDR10, but an HDR10 only TV cannot decode Dolby Vision. However, many content providers that incorporate Dolby Vision encoding in their content also often include HDR10 encoding as well, specifically to accommodate HDR-enabled TVs that may not be compatible with Dolby Vision. There doesn't need to be a winner and a loser here. Which one is better really depends on the individual's needs and habits. We should all just enjoy better-looking content in whichever format directors and creators choose to use. Okay, after brainstorming with the technical description of how Dolby Vision improves the quality of pictures, let's enjoy a 1-minute video clip that intuitively shows the before and after effect by applying the Dolby Vision technique. Well, I hope all of you have recognized the difference between the original sample and the processed one. Each demo shows how Dolby Vision strengthens image processing from 3 aspects: brightness, detail enhancement, and richer color. Those are all the topics we talked about for our presentation. This video is aiming to provide you with a basic idea of our research project on Dolby techniques. It doesn't cover all the topics in our research. More details will be included in our final report. If you are new to Dolby series, we hope this has given you a clearer picture of what Dolby techniques contributes to audio and video entertainment. Thank you for your time watching this video. We are pleased to receive feedback from you.